Okay, so capacitors and capacitance. So, what do you think? Well, what is a capacitor? It's some device that stores charge. In general, it can come with any shapes and forms, but the basic thing is you got two conductors. So two conductors, right? Not insulators, two conductors. And one of them is positively charged, the other one is negatively charged. So one of them will have positive Q, the other one will have negative Q. In general, to charge a capacitor, so you have a conductor here and a conductor here. You remove charge from one of them and place on the other. Let's say you remove negatives from this one and place on this one. So if I keep putting minus charge on this one, this becomes minus, right? And the amount of minus I remove, this becomes net positive. So this one will have positive Q, this will have negative Q. That's all. So that's a capacitor. So capacitor is the device. Capacitance will be a quantity, a certain quantity defined in a way, in a certain way which we have. So capacitance. And capacitors. So let's say I have some conductor here, and maybe another conductor there. There are two conductors, right? So let's say I keep removing charge from one and place it on the other. In general, it would be like parallel plates or something like that, not some random shape. But yeah, so you keep removing. So let's say this one here becomes net negative, so minus Q, and this one will have a positive Q, right? So there will be a potential difference between them. There is a potential difference between them. Potential difference between them. So capacitance, it has the letter C. It's equal to the following. It's just Q divided by the potential difference between them. And since we want capacitance to just be some positive number with absolute values. Okay? Capacitance is defined as find the potential difference between them, and then do the charge, the positive Q, over delta V. That's the definition of capacitance.
Will the charges always be the same as one side?
Yes, they will always be opposites. So let's talk about the units before we find capacitance for certain shapes, right? So units will be, so again, C is capacitance, right? C stands for capacitance. So the units are charge, which is in what units? Coulombs. Usually coulombs are C, but then C is here, so I would write the whole word. So coulomb. Delta V is in what units? Volts. And this combination, because a coulomb is not a composite unit, it's coulomb. A volt is a joule per coulomb, and then a joule is a Newton meter, and Newton is kilogram meters per second squared. So they're composite units. But this ratio here is given a special name. It's called 1 farad. F-A-R-A-E. Farad. Yes. In short, you can say 1 F. No, it's after Michael Faraday.
Oh.
Yeah. Okay.
Like what origin? British?
Yeah, Faraday. We will talk about Faraday's law. Yes. Yeah. Don't ask me when he was born. History is not great. So. So we'll talk about Faraday's law in about 4 chapters. So, but that's what those are the units, okay, for capacitance. Okay. So we're going to now find capacitance for different shapes. We're going to start with the easiest capacitor, which is the parallel plate, which is the one we should have in mind. Whenever you hear a capacitor, think parallel plates. So here is so parallel plates. Or a parallel plate, let me put parallel plate capacitor. Looks like this. You have a plate here and another plate here. This plate is a negative charge. This plate here has positive charge. And the distance between the plates is d, right? This is d. And the plates, they are this way, right? Plates are like this, right? In principle, it's a device, so they can't be infinite. But we would assume they are large enough that we can assume the field between them is uniform. Yeah. So this way, this is the area A. This is the area this way. And this one also has an area A, right? So the area of each plate is A, and the distance between them is D, and they have charge. In what direction is the field? This way, right? The electric field is this way. Electric field always plus the. Okay. So we will. How much is the electric field between a parallel plate capacitor? Sigma over epsilon naught, and sigma is the charge over area, right? Sigma is charge. Now, what is the potential difference between the plates? What's the potential difference between the plates? In terms of the electric field and the distance between the plates, it's somewhere in your notes. E times D. Yeah, it's E. The electric field times the distance. Yeah. And since the electric field is Q over epsilon naught A, so we can write it as Q over epsilon naught A times the distance, right? That's delta V. It's already positive, so I'm not going to put absolute values. If something is negative, you put absolute values, it becomes positive, but this one is already positive. So to find the capacitance, we go to the definition of capacitance. It's capital Q over V, over delta V. So if I do this, Q over delta V, what do I get? Fraction flips, Q cancels, right? So you get what overall? Epsilon naught A over D. Yeah. Epsilon naught A over D. If you want the capacitance to be larger, if you want a larger capacitance, what do? You make the area larger, or make the distance smaller. Smaller. And then we'll talk about the third way later toward the end of the chapter. Okay. So that's for parallel plates. This is parallel plates. Let's say we have a capacitor, just to get familiar with this before I do cylindrical. So we have a parallel plate capacitor. So the example here is this. Suppose C, the capacitance is 1 microfarad, right? Unit. Micro 10 to the minus 6. And the distance between the plates and the distance between the plates is D equal to 0.05 millimeters. So this is given. Part A, find the area. What's the area of the plates? Ideas? It's so C D over epsilon naught, right? It's a parallel plate capacitor. let's start with this. One microfarad, 1 times 10 to the minus 6. This one is 5 times 10 to the minus 5, isn't it? Which we can write as 50 times 10 to the minus 6. That cancels out. Epsilon naught is 8.85 times 10 to the minus 12. And so the area .65 square meters. That's the area of this capacity. Okay. Yeah.
Are both those exponents negative?
Oh yeah, both are negatives. Yeah, you're right. Yeah, sorry. Yeah, 10 to the minus 6.
There was a calculator.
10 to the minus 6. Yeah, even better, right? So this combination cancels that. So 50 over 8.85, which is 5.65. Yeah, so even better. So that's good. Okay. The next question is, if the potential difference between the plates is 1.5 volts, if the voltage, the potential difference, if delta V is 1.5 volts, so V, if find Q, how do you find Q? CV or C delta V. From the definition, you get it's going to be 1 microcoulomb, 1.5 microcoulomb. Okay. Next, we're going to do the cylindrical capacitor, and then we'll do spherical capacitor next time. So let's try the cylindrical capacitor. So we're going to use what we know about the electric field between two cylindrical shells, right? So here's what I mean. So what we know, so not just because we started a new chapter, we forget the stuff we learned. So it would be useful. So here is an inner cylindrical shell. It doesn't matter whether it's a shell or a solid. After all, it's a conductor, so where would the charge go? Outside. Yeah. So here is the first shell. And then the outer one is here. We have radius V. Like this. Right. And let's say the length is L. I know it's not infinite, but we're going to still use the infinite result for the electric field. It's long enough that it's this distance this way between them is much smaller than their length. So we're still going to say there is enough symmetry to use Gauss's law and so on, right? So let's say this one has plus. It doesn't matter which one has the plus, which one has the minus, because after all, we're going to do the absolute value of the potential difference. Doesn't matter. So one of them has plus Q, the other one has minus Q. As we know, the electric field for an infinite cylinder between the two cylinders was lambda, which is the charge per unit of length, over 2 pi epsilon naught little r and then r hat, right? Lambda is the charge per unit of length. Then we're going to find the potential difference. Delta V is going to be minus the integral of E dot dr from A to B. The potential difference between the two conductors. So this becomes lambda over 2 pi epsilon naught, the minus sign together. Integral of dr dot r hat just becomes dr, and then 1 over r from, and then from A to alright? That integral is what? Yeah, ln of b over a. Good. So we get minus lambda r over a over a. Let me write here delta d or the absolute value of delta d is now lambda over 2 pi epsilon naught ln of b over a. What's lambda? We said charge over length, right? So it's q over l. Q over l 2 pi epsilon naught natural log of b over a. And so capacitance q over delta. Okay, so you have that ratio. The q goes away, right? Take the ratio. And then the fraction gets q pi epsilon naught l over length over b over a. That's the capacitance. Before I go on, I was just want, let me let you write it first. I want to just mention something about capacitance. Wait. Yeah.
Is the radius A and B is very small, so you can assume that it's a linear charge density, not rho.
It does not matter at the end. It's the charge per unit of length, right?
Oh yeah.
Yeah. So if you have a tube and you just cut a section of it of some length, there is a charge over the length, right? So,
But sorry.
yeah.
Why? How if the charge is not linear? It's a area, so it's a shell, right?
I think I know what you're asking. Right? It's this is A, right? Right. And the length is L.
Yeah.
So you can say rho is what? Charge over volume, right?
Volume, yeah.
And so it's Q. What's the volume? Pi A squared.
Yes, L.
L. What's Q over L? So this is lambda over pi A squared. So lambda will just be pi A squared times rho. So it doesn't matter whether you use rho or lambda. I'm just, as long as you multiply by the length, you will have the charge in that length. So just like, yeah, it would still work. Either way. Yeah. At the end, it would be charge over something, and that something will, the charge will cancel. So is this meter stick? Does it have a volume density? Yeah, of course. But we can assume we got mass per unit of length. So if this is 1 kilogram, half a meter will be half a kilogram. I don't need the density multiplied by the volume, because I can just multiply by the length. It's quicker. Okay. I was going to say a couple things. Look at, we'll compare this. Notice capacitance, by definition, is charge over potential difference. But then charge ends up canceling, and we ended up with area over distance, right here. The area is the area of the plates, and B is the distance between the plates. So it's just the capacitance is a geometric quantity at the end. Once you construct a capacitor, you make two plates, they have a certain area and a certain distance between them. That is your capacitance. Whether it's charged or not, it doesn't matter. So just like if you have a bathtub and its volume, let's say, is 1,000 liters, whether it's empty or full, the volume is still 1,000 liters. So once you construct it, that's the capacitance. Okay? So it is a geometric quantity at the end. Capacitance. So notice this one. Area. It has to do with the dimensions of the object. Same thing here. It has to do with dimensions, right? Inner radius, outer radius, length. It has to do with the geometry of the thing. The charge, potential difference, they all cancel, and you just end up with something that is just geometric. So once you construct a capacitor, it has a certain capacitance, and that's it. Okay? Let's see. I think that was the main thing I wanted to say about this one. I have. The time will not permit to do the spherical one, but let's try to get familiar with this one. Let's say this inner radius, let's say it's 1 centimeter. Let's say A is 1 centimeter and B is 2 centimeters. If A is 1 centimeter, B equals to 2 centimeters, and let's say the length is 1 meter. 1 meter. What would the capacitance be? So the 2 pi epsilon naught times 1, right? 1 meter over the natural log of 2. Yes? For this. So for these dimensions here, if I plug them in, I would get 2 pi epsilon naught. L is 1, and then B over A, 2 over 1, 2 centimeters over 1 centimeter. It's just going to be L and B. Now, this is 2 pi over something. So you're going to end up with a number that's like 10 to the minus 12, right? Yeah. So usually capacitance is very small. It's a small number. It's like 10 to the minus 12, 10 to the minus 9. So you're going to have microfarads or nanofarads or picofarads, something 10 to the minus 12. It's going to be tiny. Okay? So usually capacitance does not, you don't have like 1 farad. Right? If you look in the back of, if you look at electrical equipment, by the way, don't say I have unplugged my dryer or washer and I can just touch everything. You can't, because there are capacitors in there and there's charge stored. And the charge is ready to discharge. And, if you touch the wrong thing, it might discharge on you. So, yeah. So we have to, be careful. Don't say I unplugged the electric equipment. There might be capacitors there holding charge. They're fully charged. And if you look in the back, you look at capacitance, it's usually a tiny number. Okay? Not farad. Farad is huge. Maybe micro, maybe nano. I forget what the numbers are, but they're small. Huh? Probably bigger. Let me pause this.